September 1944. A Wehrmacht testing facility outside Berlin. Senior engineer Klaus Hoffman approached the captured American Sherman tank with the confidence of a man who had analyzed every significant armored vehicle in the European theater. His assignment was straightforward: evaluate this American machine, identify its weaknesses, and provide tactical recommendations for destroying it. What he discovered over the next 72 hours would fundamentally challenge everything German engineering doctrine held sacred. The Sherman sat in the testing yard, its olive drab paint scarred from combat but mechanically intact. German tankers had nicknamed it the Ronson after the cigarette lighter, because it supposedly lit on every strike. Wehrmacht propaganda claimed American tanks were coffins on tracks, death traps that German Panzers destroyed effortlessly. Hoffman had read these reports. He had studied the intelligence assessments. He expected to confirm German superiority within hours. His first surprise came before starting the engine. The Sherman's hatches opened smoothly, requiring minimal force. German tanks demanded heavy pulls, sometimes requiring 2 men to operate under combat stress. Hoffman noted this in his report with academic detachment, not yet understanding its significance. He climbed through the commander's hatch, a space generous enough for a full-sized man wearing winter gear. His Panther tanks required contortions to enter. The American designers had apparently prioritized crew comfort, which Hoffman initially considered a weakness. Comfortable soldiers were soft soldiers, or so German doctrine taught. Inside, the Sherman's layout contradicted every principle of German tank design. Everything was accessible. The transmission could be removed through a hatch in the floor. The engine compartment opened from above. Ammunition racks were clearly marked and positioned for rapid access. German tanks prioritized armor protection over maintenance accessibility, requiring hours of disassembly for routine repairs. The Sherman seemed designed for field maintenance by mechanics of average skill. Hoffman documented this as evidence of American mechanical inferiority, assuming their crews lacked the technical sophistication of German tankers. The engine start sequence revealed the first crack in Hoffman's confidence. German tank engines required careful procedures, precise throttle control, and often 10 to 15 minutes of preparation in cold weather. The Sherman's radial engine fired on the second crank. No warm-up period, no temperamental behavior, just immediate, reliable power. Hoffman sat in the driver's position, studying the controls. The transmission was automatic. German tankers trained for months to master manual transmissions, developing the skill to shift smoothly under combat stress. American tankers apparently needed no such skill. The tank shifted itself. Hoffman's initial assessment was harsh. Americans had created a tank for incompetent crews, soldiers who couldn't handle real combat vehicles. He recorded this judgment, confident in German technical superiority. Then he drove the Sherman. The test course outside Berlin replicated various terrain conditions: soft soil, hard roads, obstacles, steep grades. German tanks navigated these with difficulty, requiring skilled drivers to avoid mechanical failure. The Sherman handled everything effortlessly. The automatic transmission meant the driver could focus entirely on navigation and tactics rather than gear selection. On soft ground where German tanks bogged down, the Sherman's wider tracks distributed weight more effectively. The Sherman climbed a 35-degree grade that would stall a Panther. It crossed a trench that would trap a tiger. Most disturbing for Hoffman, it did all this while consuming fuel at rates that seemed impossible. He checked the gauges repeatedly, certain of instrument error. The Sherman was achieving nearly double the fuel efficiency of comparable German tanks. This contradicted everything German engineers understood about power-to-weight ratios and engine efficiency. Hoffman ordered his team to disassemble the engine. What they found challenged fundamental assumptions about tank design. The right radial engine was essentially an aircraft engine adapted for ground use. German engineers had dismissed this approach as theoretically unsound, yet here was proof it worked brilliantly. The engine produced reliable power across a wide range of conditions without the temperamental behavior of German designs. More significantly, it was modular. The entire engine could be replaced in 4 hours by a moderately trained crew. German tank engines required 2 days of work by specialized mechanics. The implications were staggering. Americans had designed their tank not for technical perfection, but for operational reliability. Where German engineers optimized performance, American engineers optimized maintainability. Where German doctrine demanded highly trained crews, American design accommodated average soldiers. Hoffman began to understand what his superiors did not want to hear. The Sherman was not inferior, it was different, and in ways that mattered for sustained combat operations, it was superior. The armor testing produced results that seemed impossible. The Sherman's armor was thinner than German tanks, a fact Wehrmacht propaganda emphasized constantly. German 88mm guns could penetrate Sherman armor at ranges exceeding 2,000 meters. This was true. What propaganda omitted was that Sherman armor was more consistent in quality than German steel. Hoffman's metallurgical analysis revealed that American armor maintained uniform hardness across entire plates. German armor in late 1944 showed quality variations that created weak points. Pressed by resource shortages, German foundries could no longer maintain consistent standards. American industry, untouched by bombing, produced perfect armor plates by the thousand. The sloped armor design drew Hoffman's particular attention. German engineers had pioneered armor sloping with the Panther, yet the Sherman's designers had implemented similar principles years earlier. The American approach was less elegant, less theoretically optimal, but it worked. Incoming rounds deflected more often than German intelligence predicted. Hoffman fired captured German weapons at the Sherman from various angles, documenting the results. At combat ranges below 1,000 meters, the engagement angles meant many German rounds glanced off rather than penetrating. The propaganda image of Shermans as easy kills was true only under ideal conditions that rarely existed in actual combat. The most shocking revelation came from the Sherman's mechanical reliability testing. Hoffman's team drove the tank continuously for 72 hours, stopping only for fuel. German tanks required maintenance stops every 8 to 12 hours. The Tiger needed mechanical attention after every 100 kilometers. The Panther's transmission was legendary for failure. The Sherman ran for 3 days straight without mechanical intervention. When Hoffman's team finally stopped, they conducted a complete mechanical inspection. Minimal wear, no significant failures. The tank could continue indefinitely with basic field maintenance. Hoffman documented oil consumption rates that seemed impossible. German tanks consumed oil at rates requiring frequent replenishment. The Sherman's oil consumption was negligible. The air filtration system, which Hoffman had initially dismissed as overly complex, proved brilliantly effective. German tanks in Russia had failed by the hundreds when dust infiltrated engines. The Sherman's filters prevented this entirely. In North African testing, captured Shermans had operated in sandstorms that killed German engines within hours. The suspension system revealed another American advantage Hoffman had not anticipated. The vertical volute spring suspension was simpler than German torsion bars, leading German engineers to consider it primitive. Yet it was more easily repaired under field conditions. A damaged bogie wheel could be replaced in 30 minutes. German torsion bar suspension required specialized tools and hours of work. More significantly, the Sherman suspension provided a more stable firing platform. Hoffman's gunnery tests showed American gunners could fire accurately while moving, something German doctrine considered nearly impossible. The ergonomic design elements that Hoffman had initially dismissed as softness proved to be sophisticated engineering. The tank's interior was designed for prolonged operations. Crew fatigue, which German doctrine largely ignored, had been carefully considered by American designers. The seats provided actual support. The controls were positioned to minimize physical strain. The ventilation system was effective, preventing the heat exhaustion common in German tanks. After spending 12 hours inside the Sherman, Hoffman understood something profound. American designers had recognized that tank crews were human beings whose performance degraded with discomfort. German designers treated crews as components that should simply endure hardship. The ammunition storage represented another American advantage hidden by propaganda. German tanks carried fewer rounds but of larger caliber. The Sherman carried more rounds of smaller caliber ammunition. German doctrine emphasized killing enemy tanks with single shots. American doctrine emphasized sustained fire that eventually found weaknesses. Hoffman's tactical analysis revealed the American approach was more practical. In actual combat, first shot kills were rare. Sustained, accurate fire determined engagements. The Sherman's faster reload rate and larger ammunition supply meant it could maintain fire longer than German tanks. The radio equipment shocked Hoffman more than any other single system. Every Sherman had a radio. German tanks rationed radios, with many vehicles relying on flags and hand signals for coordination. The American radio was simple, reliable, and powerful enough for consistent communication. More significantly, it was designed for use by average soldiers rather than communication specialists. Hoffman tested the radio system extensively. American tank commanders could coordinate movements, call for support, and share intelligence in real time. German tank formations often fought blind, with company commanders unable to communicate with all their vehicles. The logistics analysis revealed the Sherman's true brilliance. Hoffman's team calculated maintenance requirements, fuel consumption, spare parts needs, and crew training time. The results contradicted everything German military doctrine taught. The Sherman required 1/3 the maintenance hours of a Panther. It consumed half the fuel. Its parts were interchangeable between vehicles without custom fitting. Most remarkably, crew training time was dramatically shorter. American tankers reached combat effectiveness in months. German Panther crews required nearly a year of training. Hoffman stood in the testing facility, reviewing 72 hours of data, and confronted an uncomfortable truth. German tanks were magnificent machines built by skilled engineers according to sophisticated doctrine. They were also nearly impossible to maintain, temperamental in operation, and required highly trained crews. American tanks were pragmatic machines built by industrial engineers who prioritized reliability over perfection. In a prolonged war, pragmatism was defeating sophistication. The production analysis was most disturbing. Hoffman obtained intelligence on American tank production rates. The numbers seemed impossible. Sherman production exceeded 1,500 tanks monthly at peak. Germany's entire tank production across all models barely reached 1,000 monthly. More significantly, American production was accelerating while German production declined. The industrial arithmetic was devastating. Even if German tanks achieved 3-to-1 kill ratios, which they did not, America could replace losses faster than Germany could inflict them. Hoffman's final report documented these findings with scientific precision. He concluded that the Sherman was not a superior tank in terms of armor or firepower. It was, however, a superior weapon system when evaluated as part of combined operations. The Sherman's reliability meant more tanks were operational at any time. Its maintainability meant damaged tanks returned to service quickly. Its ease of production meant losses were rapidly replaced. Its radio equipment meant American tanks fought as coordinated formations, while German tanks often fought as individuals. Most significantly, its design philosophy reflected an understanding of modern warfare that German doctrine had missed. The ease of crew training proved decisive in ways Hoffman had not initially considered. American tank schools graduated crews in 16 weeks. German training required 40 weeks. When casualties mounted, Americans could replace trained crews quickly. German formations fought increasingly with inexperienced crews as veteran tankers were killed faster than replacements could be trained. The Sherman's forgiving design meant even inexperienced crews could operate it effectively. German tanks punished crew errors harshly, requiring veteran skill to maximize capability. The spare parts logistics represented another dimension of American advantage. Every Sherman part was standardized and interchangeable. A transmission from one tank fit any other Sherman without modification. German tanks required custom fitting of many components. American supply chains could stock fewer items and support more vehicles. German logistics required vast inventories of specialized parts that often were unavailable when needed. Hoffman calculated that supporting 1,000 Shermans required less logistical effort than supporting 500 Panthers. The fuel efficiency analysis revealed strategic implications Hoffman found deeply troubling. The Sherman traveled 120 kilometers on 300 liters of fuel. The Panther managed 80 kilometers on the same fuel. This difference seemed minor until multiplied across thousands of vehicles conducting sustained operations. American formations could advance farther on available fuel supplies. They could maintain operational tempo longer. They could exploit breakthroughs more aggressively. German formations, constrained by fuel consumption, could not match American operational reach. Hoffman's testing revealed that American tank doctrine was inseparable from the Sherman's design. The tank was built to support specific tactical approaches that German doctrine did not employ. American tanks advanced with infantry and artillery in coordinated combined arms operations. They did not seek tank versus tank duels. They used artillery and air support to suppress enemy armor, then exploited with rapid movement. The Sherman was optimized for this approach. Its speed, reliability, and crew comfort enabled sustained operations that wore down German defenders. The armor quality analysis produced results that contradicted Wehrmacht intelligence assessments. American armor steel maintained consistent properties across production runs. German armor in late 1944 showed increasing quality variations as alloy supplies became scarce. Hoffman's testing revealed that some German armor, particularly from late war production, was actually inferior to American steel despite greater thickness. The metallurgical advantage Germany had enjoyed early in the war had evaporated through resource depletion and production pressure. The crew survivability analysis revealed another American design priority. The Sherman's internal layout protected crew members better than German propaganda acknowledged. The ammunition was stored below the turret ring with water jackets providing additional protection. Fuel tanks were protected by sponson armor. Crew positions had escape hatches accessible under combat conditions. Hoffman reviewed casualty statistics from captured American medical records. Sherman crews survived knocked-out tanks at higher rates than German crews survived Panther losses. American designers had clearly prioritized crew survival, understanding that trained crews were more valuable than tanks. The maintenance accessibility that Hoffman had initially dismissed proved to be sophisticated engineering. Every major component could be accessed without complete disassembly. The transmission dropped through the floor. The engine lifted out the top. Final drives could be replaced from outside the hull. This design philosophy meant field mechanics could perform repairs that required factory facilities for German tanks. Hoffman calculated that Sherman operational readiness rates exceeded German rates by 30 to 40%. More American tanks were available for combat at any given time, despite similar mechanical failure rates. The electrical system represented another area where American practicality defeated German sophistication. The Sherman's electrical system was simple, reliable, and used standard components. German electrical systems were more advanced, but also more fragile and harder to repair. American tanks rarely suffered electrical failures. German tanks frequently experienced electrical problems that disabled weapon systems. The American approach of using proven, simple technology rather than cutting-edge systems proved superior under combat conditions. Hoffman examined the weapon stabilization system with particular interest. The Sherman mounted a gyroscopic stabilizer that allowed reasonably accurate fire while moving. German tanks lacked this capability, requiring stops to fire accurately. American tankers could engage while advancing, maintaining momentum that German defenders found extremely difficult to counter. The stabilizer was not perfect, but it did not need to be. It provided enough accuracy to suppress enemy positions, force defenders to cover, and enable rapid advances. Precision could wait until the tank stopped. Firepower while moving changed tactical dynamics fundamentally. The turret traverse speed shocked Hoffman during gunnery tests. The Sherman's hydraulic turret traverse was faster than German manual or electric systems. In engagement simulations, Shermans consistently acquired and engaged targets faster than German tanks. This advantage was decisive in meeting engagements where whoever shot first often won. German tanks with superior armor and guns lost this advantage if they could not bring weapons to bear quickly enough. The Sherman's fast traverse compensated for inferior firepower through superior reaction time. Hoffman's crew comfort analysis revealed American understanding of human factors. The Sherman seats actually supported crew members during prolonged operations. German tanks provided minimal seating, expecting crews to endure discomfort. Visibility was better in the Sherman, with more periscopes and better positioning. The intercom system was clearer than German equipment. These factors seemed minor individually, but accumulated to significant crew performance advantages during sustained operations. Fatigued, uncomfortable crews made more errors. American designers had recognized this. German designers had not. The final element of Hoffman's analysis addressed the Sherman's role within the larger American military system. The tank did not operate independently. It was one component of an integrated approach to warfare that included air superiority, artillery dominance, and logistics supremacy. German tanks were often superior individual weapons platforms. American tanks were superior system components. The Sherman was designed to work with fighter bombers, self-propelled artillery, and mechanized infantry. German tanks increasingly fought without air cover, with inadequate artillery support, and with depleted infantry formations. Hoffman completed his report in late September 1944. His conclusions were professionally documented but personally disturbing. The Sherman was not a great tank by traditional metrics. It would lose most one-on-one engagements against German heavies under ideal conditions. But modern warfare was not about individual tank duels. It was about sustaining operations, maintaining readiness, replacing losses, and integrating combined arms. By these metrics, the Sherman was not just superior to German tanks, it was in a different category entirely. The Sherman represented industrialized warfare. It was a weapon designed for mass production, easy operation, field repair, and sustained combat. German tanks represented craftsman warfare, individual machines built to exacting standards by skilled workers. In 1944, craftsmanship was losing to industry, quality was losing to quantity, perfection was losing to reliability. Hoffman understood what many German generals refused to accept. America had not outdesigned Germany. America had outproduced Germany so completely that design superiority became irrelevant. Hoffman's superiors suppressed his report. The conclusions were too disturbing for German military doctrine to accommodate. Wehrmacht propaganda continued claiming Sherman inferiority. German tactical planning continued assuming American mechanical inadequacy, but Hoffman knew the truth, and it terrified him. Every Sherman destroyed was replaced within days. Every crew lost was replaced within weeks. Meanwhile, German tank losses were increasingly irreplaceable. The industrial arithmetic was devastating and final. German tank design had pursued perfection and achieved magnificent machines that were too complex, too expensive, and too rare to change the war's outcome. American tank design had pursued practicality and achieved a good machine that was simple enough, cheap enough, and numerous enough to win the war. Hoffman's suppressed report had tried to explain this to generals who could not hear it. By the time they understood, it was far too late. The captured Sherman that shocked a German engineer in September 1944 was not a better tank than the Panther or Tiger by the measures German doctrine valued. It was a better weapon system by the measures that actually determined victory.